In example 9, consider the initial value problem. dp over dt is equal to 0.08p times 1 minus p over 1,000, where p of 0 is equal to 100. All right, notice, of course, that we have this differential equation is one that models logistic growth. It fits that bill. And then we have an initial population here of 100. A couple things about our differential equation. This 0.08 is our k value. And the 1,000 down there at the bottom is our carrying capacity, right? The biggest that population can get. Part A, find the size of the population at time t equals 40 and t equals 80. In order to do that, you can't do that from the differential equation. You have to do that from the actual equation. But that's no sweat because we've already solved it. We know what it looks like. All we have to do is fill in the gaps, fill in the little puzzle pieces. Okay, and then we can plug in 40, we can plug in 80, it'll be a piece of cake. Part B, at what time does the population reach 900? Again, I need the equation, which we will get from part A, and then we can set it equal to 900. Part C is going to be, hopefully, the easiest part of this. Find the limit as t approaches infinity of p of t, assuming that p of t is the particular solution to that initial value problem. It might have, like, before all of this started, you were looking at this blindly, you might have saw that and was like, how am I supposed to get that when I have the differential equation? But we know exactly how big that population is supposed to get. Part D, what is the size of the population when the growth rate is at its fastest? Again, it's one of those very common things, Part C and Part D, very commonly asked if you have a question that involves logistic growth. So let's set about actually trying to solve this thing. So I'm going to go ahead and take a moment and, on example 9, rewrite my differential equation. Let's see if I remember it. dp dt is equal to 0.08p times 1 minus p over 1,000. And then we have our initial population of 100. Okay, so let's go ahead and label some things about this thing. What's this 1,000 down here at the bottom? This 1,000 is the carrying capacity. I want to be able to recognize that right off the bat because it's going to be a key component in our logistic growth model. And the other thing that I want to be able to recognize is our constant of proportionality, our k value, because both of those things play a part in our equation. Speaking of the equation, let's go ahead and write it. It's supposed to look like this. Our population over time is equal to our carrying capacity over 1 plus some number b e to the negative kt. And like I said, we already have this and we already have that, the L and the K. We just need to figure out what the B is. And you know what? We already derived a formula for what the B is too. It's back over here too. L minus the initial over the initial. It's almost like a percent error or percent change or something like that. Okay, so we've got P of t, our actual equation, is equal to carrying capacity of 1,000 over 1 plus b e to the negative 0.08t. Only thing that's left is to figure out what b is. B is equal to carrying capacity minus the initial over the initial. Let's say, for example, in the heat of the moment, you completely forgot that. What could you do? Well, what you could do is just plug in 0 for t and set the thing equal to 100, and then you can easily solve that thing for b like we did originally. All right, so solving this down, I'd have 900 up top over 100, which is equal to just 9. B value is equal to 9. So writing one more time, because 3 times wasn't enough, we've got 1,000 over 1 plus 9 e to the negative 0.08t. And there's our logistic growth model. Are we done? I think I said model with a T. Anyway, no, we're not done because we want, what's the population at t of 40 and t of 80. So that's pretty much a calculator kind of exercise. So we break open the calculator. Let's start a new one here. And actually what I'm going to do is I'm going to split screen this thing. Looks like I can split screen with a stopwatch. That seems kind of handy. All right, so I'm going to add a graph screen on this side, and I'm going to add a calculator screen on that side. I'm going to do both things on the same screen. All right, over here on the graph, let us add in our equation, which was 1,000 on top, 1 plus 9 e to the negative 0.08 t, in this case x, enter. And it looks like I'm seeing a whole bunch of nothing. And the reason why is because I need to zoom in a little bit, or really zoom out. All right, so there we can see it, and it tops off at this asymptote here at 1,000, right? That's our carrying capacity. That's right there. You can see that sigmoidal graph. Over here, we wanted to just plug in 40, plug in 80. So I need my function, plug in 40, hit enter. And we get about 731 or 732, whatever these things are. It didn't even tell us, I don't think. So this one is about 732 individuals. Individual what? All right, and then we'll do the same thing. You like that approximately equal sign? I practiced them. Let's do the same thing and then just plug in an 80. Will it be twice as big? No, it can't be twice as big because it can't get bigger than 1,000. Oh, and we're pretty close. So we got about 985 here. About 985 individuals for each of those. Okay, let's look at part B, shall we? If I'm not mistaken, part B asked us, when is the population equal to 900? Is that right? Yes. So we're just going to set our equation that we solved right up here, or that we derived right up here, equal to 900. And then the rest of this is 100% algebra. Okay, 1 plus 9 e to the negative 0.08 t. We're solving that thing for t, obviously. Let's go ahead and cross multiply that thing, and I'm going to have 1 plus 9 e to the negative 0.08 t is equal to 1,000 over 900. Cancel out some zeros, and we have 10 over 9. I'll subtract over the 1. 9 e to the negative 0.08 t is equal to, if I subtract 1 from this, it's like subtracting 9 over 9. That's going to give me 1/9. Divide both sides by 9. Dividing both sides by 9 is the same thing as multiplying by 1/9. So I'd have e to the negative 0.08 t is equal to 1 over 81. And I have an exponential equation. To solve the exponential equation, get rid of the e. I take the natural log of both sides of that thing, and I'll have negative 0.08 t is equal to the natural log of 1 over 81. Last step is to divide over negative 0.08. Calculator time. It was the natural log of 1 divided by 81, get out of the parentheses, divided by negative 0.08. Approximate that. And we got about 54.931. Since this is like the other ones where population makes sense to kind of round that to the nearest whole number, but this is a time value, so we can have fractions of time for sure. Fractions of people, frowned upon. 54.931. Times, days, hours, I don't know. It didn't tell us what that time unit was. All right, part C was this. Part C is what I'm telling you is, that shouldn't have been pink. It's throwing me off. Should be this. Really? Really? Okay, anyway. Part C is this. It's the limit as t approaches infinity of our equation P of t. Well, as time increases, let's just take a look at the graph we got there. Collapse that thing down. Then we're getting closer and closer to this asymptote, and that asymptote happens at its carrying capacity. And I want to know that right off the bat. I want to understand that when I take the limit as t approaches infinity, that is just its carrying capacity of 1,000, and it's done. There's nothing else to do. except for part D. So part D should be equally, look, there we are again with the pink line. What's going on? There we go, that's better. This one is, when is the growth rate the fastest? Well, the growth rate is the fastest when we're at half of the carrying capacity. That is at its point of inflection. So we're going to increase until we get right there to its point of inflection, and then it's going to start to decrease. If this is L, then that number right there is 1/2 of L. Our L value is 1,000, so we want half of 1,000 to get 500. So when our population is 500, we should be at maximum growth rate. So when P is equal to 500, the population growth rate is at its fastest. And I could see conceivably that they might ask you that particular question, or they might ask you at what time does that happen. And then you would just do exactly what we did in part B, but instead of setting it equal to 900, you'd set it equal to 500, half of its carrying capacity. All right, then that finishes off that particular example. We're going to take a look at another one in the next video.